Hello students, now I'm going to teach about the carbocation rearrangement. And first of all, let me explain about a little bit of carbocation. Carbocation. What is carbocation? They are the solid species which have only 6 valence electrons after sharing and whose carries a unit positive charge. Carbocations, they are solid species which carry a positive charge and only 6 valence electron after sharing. Say, let's take an example. It is formed by the hydrolysis cleavers. Now let's take an example. This is carbon, and this is carbon, and this is halide, and we split the bond by hydrolysis fission, and this X halogen group. This halogen group is more electronegative than this carbon. And then we have 1, 2, 3 bond. It is positive charge carbocation, and another one is negative charge. That is, it acts as a nucleophile. And then we have to discuss regarding the rearrangement of carbocation. We have already known that the carbocation, they are the positive charge which carry 6 valence electron after sharing. That is valence electron 1, 2, 3, 4, 5, 6. Electron deficient. They are an electron deficient group. Then, okay. Then, rearrangement of carbocation. Rearrangement of carbocation. Why do we need to rearrange the carbocation? In order to get the stability of carbocation, we have to rearrange the carbocation. So, most stable carbocation is tertiary, third degree, then the secondary, that's one is primary, and the methyl carbocation. Methyl carbocation is the least stable. So let's take an example. CH3, CH2, CH carbocation. This is primary carbocation. But if there is any possibility to rearrange that carbocation, we have to rearrange by shifting hydride shape. 1, 2, hydride shape. 1, 2, hydride shape. In order to get the stability of most stable carbocation, we have to shift one of the hydride. So this hydrogen, this is carbocation, and this hydride can shift to this electron deficient carbon atom. So we get CH3, CH carbocation, and CH CH2, CH3. Then this is secondary carbocation. So primary, this is primary carbocation and this is secondary carbocation. So if we compare to this group, secondary carbocation is more stable as compared to primary carbocation. So we have to rearrange that hydride shape. Then this is example number 1. And then let's take an example number 2. Example number 2. CH3 C okay CH3 and CH3 CH2 carbocation. This is primary carbocation. The primary carbocation, but there is a possibility to rearrange carbocation by shifting a methyl group. This methyl group can shift to this electron division carbon atom, and then CH3 carbocation, CH2 and the CH3. This is tertiary carbocation. Tertiary carbocation. 1 to methyl shift. 1 to methyl shift. And then let's take an example. So this is a phenyl group, this is a methyl group, and this is a phenyl group, and this is okay CH2 carbocation. Same thing. This is also a primary carbocation, and we can shift the phenyl group to this electron division carbon atom. So we get CH3C carbocation. CH2 is a phenyl group and is also a phenyl group. This is a 1, 2, 3 tertiary carbocation. Tertiary carbocation is most stable because there is more resonating structure. More resonating structure. So tertiary carbocation is more stable as compared to this primary carbocation, because this species will have more resonating structure as well as hyperconjugation. Then this is phenyl shape and methyl shape. Another example, let's take an example which have both of CH3 CH3 CH2 carbocation. Here, regarding the rearrangement of carbocation, there is a two possibility for shifting of either it may be this methyl group or this hydride group. We have two options. If we shift the methyl group first, 1 to methyl shape. We choose the methyl shape, then we get CH3 C, this one methyl shape, plus CH2 CH3. We get a 1 to secondary carbocation. Then, there's another case, if we shift this hydride to this one, CH3 carbocation, CH3. This is also a tertiary carbocation. If we this is secondary carbocation and this is tertiary carbocation. But as compared to the secondary carbocation, tertiary carbocation is more stable because it will have more resonating structure as well as hyperconjugation effect. These methyl group, they are the electron donating group. I mean the plus I effect. Stability of carbocation is directly proportional to what? Plus I effect, as inversely proportional to minus I effect. That's why this tertiary carbocation is more stable than secondary carbocation. Let's take an example. Okay, let's take an example. CH3, C, CH3 phenyl group, and CH2 carbocation. Here, there are also a two possibility regarding the rearrangement of carbocation. First, 1, 2 methyl C. Next, 1, 2 methyl C. This one. Then another one is this phenyl C. 1, 2 phenyl C. First, let's do it by the methyl C. CH3 C carbocation, this is phenyl, and CH2 CH3. This is also a tertiary carbocation. And again, let's do it another part way, that is CH3 C CH3 carbocation CH2 phenyl group. Here, this is also a tertiary carbocation because this positively charged carbon atom possesses 3 carbon atoms. So, this is a tertiary carbocation, but this is also a tertiary carbocation. Both of them have they are the most stable form of carbocation. But as compared to this species, as compared to this A and the B group species, how we are going to identify the most stable carbocation? Say, based on the migratory aptitude. Aptitude, we can differentiate the most stable carbocation. The most stable carbocation. And what is migratory aptitude? Migratory aptitude is hydride most stable, next phenyl, next tertiary alkyl group, next secondary, next primary. The preference is the setting of the preference, the setting of carbocation. The most preferred is hydride. Hydride is the most preference for the setting of carbocation. Then phenyl. So methyl is the least stable based on the migratory aptitude. Methyl is the lowest preference. So we have to seek this phenyl group. We have to this phenyl group. So we get tertiary carbocation. So based on the migratory aptitude, this compound B, this species compound B is the most stable product regarding the migratory aptitude. Then let's take an example. It's okay. Let's take an example question. This is benzene toluene A, OH is this B, then and this is a nitrobenzene. Which one is the most stable? This is toluene and the phenol and the nitrobenzene. Which one is the most stable? The most is C. The most stable is this phenol. Phenol. Why? Why phenol is most stable? Why? Phenol have the oxygen have two lone pair. So these two lone pair can donate to this benzene ring so as to get stabilized. So this lone pair electron can donate to benzene ring, thereby stabilizing this benzene ring. I mean the delocalization of the pi electrons. So this will have the more resonating structure. And this is nitro group. Nitro group is an electron. Nitro group is an electron withdrawing group. So this nitro group withdraws the electron from this benzene ring, thereby destabilization of this benzene ring. So the most stable form is regarding the carbocation, this B. Then this is toluene. This is a methyl group. The methyl group is an electron donating group. So A, and the last one is the C. This is minus I effect. This is plus M effect. Plus M, positive resonance effect. So I mean, as I already have mentioned before, stability of carbocation is directly proportional to plus I effect and inversely proportional to minus I effect. This has positive resonance effect or mesomery effect. This is minus mesomery effect. I mean this is negative inductive effect. Okay. Then let's take an example. Another example. CI3. No. Let's take another example. Okay. This is carbocation. This is a carbocation. Another example. And this is carbocation. This is also a secondary carbocation. This is also a secondary carbocation. But which one is? If we compare to this group, this is suppose let's take this group as a group A and B. This group A and group B. As compared to these two groups, which one is the most stable? But however, they are the secondary carbocation, and this is also a secondary carbocation. Among these two groups, which one is the most stable? The most stable is this, because we have this is hydrogen. We can shift that hydride to this carbocation to get this carbocation. This secondary carbocation, but this secondary carbocation, I mean the distance, based on the distance with minimum distance to the more resonating structure compound. This carbocation have maximum far apart to this benzene ring, and this carbocation have minimum distance from this benzene ring. So minimum distance with benzene ring will have more stable carbocation. So this structure will have the most stable carbocation as compared to this group A. Then Another example, okay, let's take another example. 1, 2, 3, 4, 5. 1, 2, 3. And this is a 1, 2, 3, 4, 5. This is a carbocation. This is also a carbocation, and this is a carbocation. This, let's suppose let's take A and the B. Which one is the most stable? This is also a 1, 2. This is a secondary carbocation. This also is secondary carbocation. Secondary carbocation. All of them have a secondary carbocation. Secondary carbocation, not a tertiary carbocation. But which one is the most stable among these two secondary carbocation? Based on the alpha hydrogen atom, it can be identified or it can be distinguished as based on the number of alpha hydrogen atom. We can distinguish the most stable carbocation based on the number of alpha hydrogen atom. More is the alpha hydrogen atom, more is the stable form of carbocation. More is the alpha hydrogen atom, more is the stable form of carbocation. This group A have 1, 2, 3, 4. 4 alpha hydrogen atom. 4 alpha hydrogen atom. 4 alpha hydrogen atom, and this 1, 2, 3, 4, 5. 5 alpha hydrogen atom. More alpha hydrogen atom will have the more stable form of carbocation. So these two group, I mean this is secondary, this is also a secondary, and this is also a secondary carbocation. But the last one, group B, is the most stable carbocation because it have more alpha hydrogen atom as compared to this group. Okay. I hope that you will understand to this group. If you have any doubt, you can ask me or whatever. Please feel free. You can ask me regarding this rearrangement of carbocation. Okay.